Hello, this is Joe Bacos with this week's edition of the Taurus Report. Welcome. This week I would like to look at the large-scale structure in the universe and actually a little segment on the fine structure that the Webb telescope is showing exists in the structure of galaxies, like a close-up look at a galaxy. So I'll look at those two things today. And I am also going to be presenting some of the information that is discussed by a friend of mine, Lee Greer, and he has a website that is the enlightenmentlegacy.net, and I will be sharing that with you. He has done some excellent work. He is an amateur astronomer like myself, not by profession, but just by a very active interest. So we will be taking a look at all of these things today. First, I would like to take a look at a galaxy that the Webb telescope has just seen, and you can excuse me, you can find this article if you look at the new general catalog. If we just go into Google and do NGC 7496, that's the name of the galaxy that they were just looking at, and JWST, and if we do a search, and let's click in the news, right, and you take a look at this galaxy, and I will put the link in the comments section of the video. So we see these kinds of very intricate structures within a galaxy that previously, when looking at distant galaxies, telescopes were not able to resolve. And you can see it all looks sort of like foamy. Now this is all rotating. And we have all this intricate foamy structure. And the thing about this, to me, is that with standard gravity, which is unidirectional, like there's only attraction. And there isn't a variation in the form of the law with distance. The form of the law stays the same with distance. And so to me, it's difficult to see how you can get such a structure that is billions of years old and having this intricate foamy rotating structure to it. But this is something that is very prevalent and obvious in cyclic gravity and cosmology, CGC. I have shown this video before, but I would like to show it to you again. And this is the video that I did a few years ago that is a simulation of the formation of a solar system to kind of show what I mean. If we take a look at this simulation, and if you run the simulation, and again, I'll put this link in the comments, if you run this simulation, you end up seeing that even with something as simple, relatively simple compared to a galaxy, I mean, even as something as simple as a solar system, you get all of these very complex paths that over time, when the structure is in gravitational influence over a great deal of time, then eventually it settles out into circular orbits. That's why I say in a solar system, there's a strong pressure towards circular orbits over time. And I believe the same thing for galaxies, but for galaxies, the time scale is much, much larger. And we see it ultimately in structures like Hoag's object, which I've shown you before. Hoag's object here. And this is on the scale of a galaxy. So I am assuming that over a great deal of time, much larger time scale than on a solar system. You also are going to have this emphasis on circular structure. And as I've shared in a in a prior video, I have shared that we see these sort of shells, even in elliptical galaxies, that are of a more haphazard shape than disk galaxies. We still see this tendency towards circularization. But germane to the point I'm trying to make right now is that in the earlier stages of a galaxy, we're going to see lots of very complex movements and very complex foamy structure under CGC, whereas all of this kind of structure is very difficult to explain with standard cosmology. Now, transitioning to structure on a much larger scale, on the scale of the universe and what it means for various cosmological models, I would like to share some of the things that my friend Lee Greer points out at his website. So I want to remind you how to get to my website. If you type in Torus Report, all one word, .com, and put that in a Google search, then my website will come up. And I've added a page that takes you to Lee's website, where he presents standard cosmology as sort of like a new Ptolemaic system. And what he means by that is that the Ptolemaic system, if we go to his site, used a lot of free parameters in these epicycles in order to explain planetary motion. And he does a very ingenious demonstration here that if you have enough free parameters, then you can make any shape you want. And so your cosmology is pretty liberated if you have all these different free parameters that you can play around with. Then you're able to explain a lot of things. Now, of course, we'd like to get to a more elegant cosmology that doesn't take advantage of all these free parameters. And so Lee presents standard cosmology as sort of like the new Ptolemaic system, wherein what we have is the hot Big Bang theory. The way that it became ascendant is taking advantage of these free parameters. Well, what do I mean by that exactly when I say free parameters? And I've discussed this in prior episodes, but let me just run through a bunch of them. Okay, so in standard cosmology, first of all, coming up with the idea of universal expansion that Einstein inserted into general relativity with a constant. He posited that the universe is steadily expanding without explaining any kind of physical mechanism or cause for that. And he posited that so that he could explain why the universe under general relativity didn't just simply all collapse in on itself. So we need this. In general relativity, this is needed, this idea of a constant expansion. Well, when we looked out into the universe in the time of Hubble, we saw that all distant galaxies, or most of them, are redshifted, suggesting that they're accelerating away from us. And this seemed to fit the bill exactly. But I call it still a free parameter in this sense, is that there is, in my opinion, no good explanation of this. I mean, you can say it's negative vacuum pressure. You can say it's a form of dark energy causing it. All of that is just simply saying that we need some explanation that the simple, well, not simple, but the physics that we see in particle accelerators, physics limited to what we can observe in experiments, cannot explain this. Right? So we just call it dark energy because we can't explain it. We're not detecting any kind of energy. And so in that sense, to me, it is a quote-unquote free parameter. okay, where you're just saying, okay, these things just do this, and we come up with a parameter to say that it does it without really explaining why in any way. Now, another free parameter in this sense is inflation, because all inflation means is that in the very early universe, we need a different expansion rate, a rate that is many orders of magnitude larger than the Hubble expansion rate. We just need a totally different expansion rate to explain how matter throughout the universe is distributed in the fine way that it is. So once again, some process is introduced that is a description. Inflation is a description of the expansion of space, but there's no explanation of why or how. It's just saying, okay, for our model to work at this very early stage of the universe, we need that it must have expanded like this. And there's no link whatsoever to any known form of physics that we see in particle accelerators. It's just declared we need it to keep our theory consistent, so we're just going to declare that it happened. So that's another example of a free parameter. Another example of a free parameter is the introduction of dark matter. Dark matter is introduced because otherwise the fine structure shown by the power spectrum of the CMB cannot really be explained. And also dark matter is introduced to explain galactic rotation rates. And once again, to me, you're just saying, if you use dark matter, you're just saying, at this place, I need an attraction that physics that we see in particle accelerators, physics that we can experiment on, cannot explain this attraction. So I am going to declare that there's some mass there that I cannot detect, and I'm going to put the mass in the shape and in the densities and concentrations and locations that I need to explain attractions where otherwise my theory would break down and I could not explain it. So all of these things are what I'm calling free parameters. And to me, they are like the epicycles in the old Ptolemaic system, where whenever motions could not be explained, these back and forth motions that we observe that planets do, over years and months in the night sky, we see them move back and forth, in contrast to the way stars always move in a uniform way and in the same direction. The planets, if you focus on them, they sometimes have like retrograde motion. And so epicycles were introduced in the Ptolemaic system to explain that. So I think there are a lot of parallels to standard GR-LCDM theory, where all of these free parameters that they're introducing, to me, are just like the epicycles. They're just, when you see motions that you cannot explain with known physics, then you start making up various, to me, imaginary energies, imaginary masses, imaginary processes like inflation, and just insert those at will within your theory in order to explain observations. And honestly, to me, that is not scientific. If you're positing imaginary things to explain your observations, that's sort of like giving up on trying to find out what's really going on, right? Because you can put all kinds of, if expansion and inflation provide pushes and dark matter provides pulls, well, all of physics is about pushes and pulls. And so if you can introduce unexplained pushes and pulls wherever you want in physics, well, then you can explain everything that way. And conveniently, there's no way to test these things because they just declare, oh, well, we can't detect them. And it's like, okay, then is that really a scientific theory? Anyways, to continue now, I'd like to look at some of the large-scale structure conundrums or mysteries or challenges, whatever you'd like to call them, various large-scale structures that we see in the universe that really challenge GR-LCDM and the Big Bang cosmology. So again, from the Torus report, if you click on this link up here, New Ptolemaic System, it brings you to a page where you can get to Lee's site. And I find this first initial picture here is fascinating to me, just because it's kind of interesting, because this schematic is sort of what I am saying is reality in CGC. So this sort of reddish sphere at the outer edge of the universe. In CGC, this outer edge of the universe is actually gas of exactly what type, I'm not sure. I mean, I call it a type of intergalactic medium, but I have to be careful because out at the outer edge of the universe, when I say intergalactic medium, I'm not talking about the medium like in between galaxies, like closer into us in the universe. I am claiming that at the outer edge of the universe, there is a gigantic expanse of gas and dust, and I'm assuming ionized hydrogen, whatever it is. What I am claiming is that the CMB is light that travels from within the universe out to this sort of segment of the intergalactic medium, where light travels through such a huge expanse of this intergalactic medium that eventually it's going to be absorbed and re-emitted. So Compton scattering or reverse Compton scattering. And because this is so thick, I don't know how many megaparsecs thick, no light would ever escape the universe, in that if you could be outside the universe, it would be dark because no light would escape it, because this intergalactic medium is so thick that all light is absorbed and re-emitted, and none of it ever escapes to the outside. So with that, in CGC, this sort of schematic that appears at enlightenmentlegacy.net is really neat to me. I like it. So it portrays this red glow here as the CMB, which in standard cosmology is depicted as the afterglow of the Big Bang. And so in standard cosmology, this is a little different in that this outer edge is really, we're seeing the Big Bang. Well, how can that be? Because in standard cosmology, space itself is expanding, and it's expanding at an accelerating rate, meaning the things furthest from us are expanding at an even greater rate. The space is expanding, I mean. And so this means when we look back in any direction, we're also looking back in time. And so it is possible to look in any direction and see the Big Bang, because every point in space was at the Big Bang. And so since you have this constant, like first inflation and then expansion, every point in space was at the Big Bang. And so the universe, in a sense, doesn't really have a center, because every point was the center. And so it's just constantly expanding. So under standard cosmology, this red afterglow is a relic or a remnant, or we're seeing the afterglow of the Big Bang. Well, in CGC, or in static cosmologies, this is very different. Okay, in a static cosmology, light goes to the outer edge of the universe, and through Compton and reverse Compton scattering, it makes its way back to us. And so we see this glow in every direction, no matter which direction we look. But what it represents is something very different than in standard cosmology. And so here I want to say something about static versus non-static cosmology. So standard cosmology, GR-LCDM, is not a static cosmology because the universe has a beginning and it's going to be expanding forever. And so it is not the same throughout time. Now, a static cosmology holds that the universe's basic shape and structure and form has been constant and not changing over time in a directional way, like where there's some set beginning and then you have this constant change. Now, in CGC, because depending on the distances that galaxies and galaxy clusters are away from each other, if they are at close distances, they may feel an attraction. Like, let's say, between us and Andromeda, there's an attraction. That's the nearest galaxy to the Milky Way. There would be an attraction. Most galaxies are within a galaxy cluster wherein they can feel attractions to other galaxies. Now, if you get beyond that scale, under CGC, there would be expansion, but not in the sense of stretching or deformation of space. In CGC, there is actually a push because at those scales, galaxies become repulsive. And so galaxy clusters may be pushing away from each other. And the reason why standard cosmologists are sort of tricked into thinking that space itself is expanding is that these distant galaxies are, in fact, accelerating away from us. And so that is being interpreted as the expansion of space, whereas under CGC, that is not expansion or deformation of space. It just means that there is actual acceleration away from us because of repulsive gravity. Now, under CGC, these galaxies and clusters will get to a distance when it's large enough, gravity will turn attractive again because gravity is like a waveform. It varies as a waveform. So the absolute value of the force, without a directional component, it is decreasing with distance, but you do have these little waves, and so in certain scales it can increase for a short time. Okay. But anyways, to make a long story short, the galaxies would be entering an era of attraction where they would slow down and then start moving towards each other again. It would be an era of contraction, okay? And then when they hit a certain distance, then they'd feel repulsion again, and then they would start being forced away again. And so under CGC, static might be a little bit of a deceptive way of saying it. I mean, it is true that under CGC it's like overall static, but in CGC you have these eras of gentle expansion and gentle contraction, okay, depending on the distances that galaxies are away from each other. Now, if that is the case, why is everything distant redshifted? Under CGC, once again, and I spoke about this in a prior episode as well, under CGC, tired light, I believe, it has been disproven that all of the redshift being the cause caused by tired light. In other words, tired light cannot be an explanation for all of the redshift. I do believe that tired light does explain part of the redshift. And this explains why there's an overall tendency to see everything redshifted no matter where we look. But I think that close analysis of this will show that there is variation in the redshift, and it is not constant everywhere as depicted in standard cosmology with the Hubble constant. With all of that said, let us continue exploring large-scale structure and its meaning. So overall picture of the universe under CGC is sort of like this if you interpret these outer regions as a very, very long expanse of ionized gas. Now, getting back to the Torus Report site, so that is the general web page, enlightenmentlegacy.net. Also, there is this page that concentrates specifically on large-scale structures and what this means for cosmology. And so if we click on that link, it brings us to a little bit different page that concentrates on large-scale structures and what does it mean. And this is the basic idea here. If one is going to posit that the universe is 13.8 billion years rather than being an eternal universe, if one posits that, then it would mean that on a certain scale, structures that are large enough, if you see some structure that is huge, that takes a long time to form, then it would challenge the idea of the hot Big Bang. It would challenge it because a structure that large would not have time to form. And some of these structures, when we look at them, from what we know of the way physics operates, a structure that large to form would take maybe 100 billion years to form. So let's take a look at some of these structures that astronomers see. So scrolling down on this page here, one of them that I would take a look at is this discovery here, where this paper written by Hunt and Sarkar, let me get to that paper real quick. So, and again, I will put all these links in the comments. So if we go to that paper, in this paper is coming from 2009. Hunt and Sarkar, they did a study trying to figure out how big of a structure can standard cosmology allow. And so we can see that they found an upper limit of between 250 and 300 megaparsecs as the largest possible structure size that you can have under standard cosmology. Anything that has a structure larger than that, then it simply would not have time to form. So what are some of these large structures that cannot possibly have formed in time to validate standard cosmology? Let's take a look at some. The large quasar groups. Let us take a look at that. So here is a paper that from 2012. And again, I'll put the links in the comments to these papers. So it's a particularly large quasar group that has been identified. And this, the size of this thing is on the order of 1,240 megaparsecs. Now, notice we just said that anything above 300 megaparsecs simply has not had time to form. And so this is an example of something that is just, it is not consistent with excuse me. It's not consistent with Big Bang cosmology. A little Freudian slip there. I live in Big Bear Lake, California. So I meant Big Bang cosmology, not Big Bear cosmology. So what is another example, another structure that we could take a look at? The Sloan Great Wall. That is another structure that is simply too large. And so here we can see various, and there's links to various looks at, it's not just the Sloan Great Wall, there's the Southern Wall. There's several of these walls, and what these walls are is exactly what it sounds like. In space, we have these giant walls of galaxy clusters, and they are just simply gigantic structures. And so given the proper motions of the galaxies forming them, there just simply has not been time in standard cosmology for such large structures to have formed. The last item I'd like to take a look at as far as large-scale structure in the universe just is a violation of homogeneity. And what I mean by that is under standard cosmology, there's this assumption that the universe, in whatever direction you look at, is roughly speaking, not exactly, but roughly speaking, homogeneous in whatever direction you look. Now, this paper that I'd like to look at next, let's take a look at this one. And this was published in a Russian journal. And so what they did with this is they took a bunch of different surveys, and I'm not going to name all the surveys. Again, I'll include the link in the comments, and you can take a look at the paper yourself. Is it just looking out into the universe in two different giant surveys. One is like an angular section of the universe here, and each dot in this diagram here, each dot represents a galaxy. And you can see that there's obviously structure to this. In other words, it's not just random. If you look out into the universe, you see different clumps, filaments, and so forth. Kind of a foamy structure, as I described earlier when you do a close-up just of a galaxy. Well, the universe overall has kind of a foamy structure too. And this is a kind of an angular look of a section of the sky. Then there's another look, which is this dark line, which is called the pencil strip, I think they call it. It's like a pencil beam. They call it that just because it's a narrow look at a very specific segment of the sky. And then they analyze this mathematically in this sense. What they were trying to look at was this. If you look at any specific direction in the sky, and then you consider along your line of sight, along the line of sight are galaxies roughly evenly distributed. Or is there some structure to that? In other words, are galaxies clumped, like closer together sometimes, and then do you run into spots where it's empty of galaxies? And so this itself is a variegated structure that the universe has, and this is even larger than any of the other structures we talked about because it covers the whole universe essentially. And what they found was, and this sort of right-skewed bell curve here would be, if it was homogeneous, would be along this line here. And the gray areas shows where there are either overcounts or undercounts of galaxies. In other words, there's a violation here of normalcy. And we see, interestingly enough, it's sort of a wave-like form. If we scroll down, there's another way of kind of depicting this. And there's several diagrams depending on what direction you look. And once again, in this diagram here, the stuff above zero means there's more galaxies than expected. and stuff below 0 means that there's fewer galaxies than expected. And notice that this isn't random. Okay, this is like a sinusoidal type of diagram, which to me, the sinusoidal form is interesting because to me, and for those of you not big into mathematics like I am, sinusoidal just means wave. Okay, so if somebody says sinusoidal form, it just means it's in the shape of a wave. Since under CGC gravity is in the shape of a wave, you'd expect to see variances in many different measurements that would have a wave-like characteristic. And so when you see this sort of sinusoidal distribution of galaxies along the line of sight, no matter what direction you look in, this is also a pattern that is difficult to explain how that could be formed in the time scale of 13.8 billion years. But if you're presenting a static cosmology, it makes perfect sense. And if you're presenting a CGC cosmology, seeing sinusoidal forms crop up also makes sense. That is it for large-scale structure of the universe. There's a couple of other items I just want to mention today. And one of them has to do with the Hubble constant, because a big part of that phrase is, quote-unquote, constant. So standard cosmology presents this sort of uniform expansion of the universe, with maybe now, because of the Hubble tension, various standard cosmologists are proposing breaking that apart maybe into one or two more eras where the expansion rate differs, which to me, again, is another arbitrary tweaking where you're just declaring that the expansion rate, you can change it in various eras whenever you need to, just to make the theory all hold together, which, again, to my way of thinking, that's not really scientific reasoning, in my opinion. But in any case, the point I want to raise now is that some scientists have noticed that the Hubble expansion rate is not uniform. Leaving aside the recent Hubble controversy, let's take a look at a paper that was published, and there are others, but let's take a look at this paper here. And so this was published a few years ago. And it's just simply looking at, in this paper, by Colin and his colleagues, they just looked at various directions, out into the sky, out into the universe. And they just wanted to measure just one item, okay? Looking at various objects, in various different directions, all through the universe. Is this expansion rate actually constant, or do we have non-homogeneity, which just means, does it change depending where you look? And in this paper, they found that it actually changes. It's anisotropic. And so, to me, this also presents a huge problem for standard cosmology. Now, the last thing I'd like to look at today, to switch gears and come back to the scale of a galaxy. For the large-scale things I've been mentioning, we've been talking about, things on the scale of the whole universe. But now I want to come back to the galaxy and just something else that Hubble kind of noticed when he was looking at the structure of galaxies. And this is simply the Hubble sequence. So what is this Hubble sequence? When Hubble looked at the various types of galaxies, he did this sort of classification scheme where galaxies start out kind of like this, as sort of a spheroid or elliptical type galaxy with a vague shape, and it goes through this kind of sequence. And then up here, it goes in one of two directions. Either being kind of like a standard disk galaxy up in this direction, or more in a spiral arm galaxy with a bar, like down in this direction. And so we see this sort of, under Hubble's proposed scheme, we see this sort of classification scheme for galaxies. Now, this presents a problem again with what we're seeing in JWST, the James Webb Space Telescope. And the problem is simply this. If you look back to the early universe, and you are supposedly getting near the hypothetical Big Bang, then what we would expect to see in the very early universe are galaxies down here, either misshapen or vaguely formed, or, what have you. We'd expect to see in this early part of the tuning fork, we would expect to see more of those and fewer fully formed galaxies as you get nearer to the Big Bang. And we're talking about, getting very close, within a few 100 million years or so. But instead, what we're seeing from Hubble is the same sort of variety of galaxy types that we see today, which to me is another argument in favor of moving to a static cosmology, or a slightly fluctuating cosmology as you have in CGC. Well, that is it for today. I want to thank you all for tuning in to the Taurus Report this week, and I look forward to seeing you again next week, where we will look at whatever is most recent in what Hubble is finding. So thank you all once again for tuning in, and goodbye for now.